Well, first I would like to thank the organizer of this workshop, and I really like this idea of an IMPA-Bath workshop because Bath is the first place where I started to do research. I did my master internship there. What I will talk about today is mixing time and cutoff. For bias card shuffling and ASEP. Okay, and this is joint work with Cyril Labbé from Paris. So, okay, I will start with a bit of motivation and a background for people that are not familiar with that kind of problem. Let's imagine that you have a box, okay, with two compartments, one which is full of particles and the other which is empty. And you know that if you somehow break the separation, what will happen after some time is that particles will spread uniformly in the box, okay? Okay, you have to conserve the number of particles. Okay, except that there are many more particles, and what we want to understand is, well, we have to we want to have some quantitative and qualitative understanding of how this happens. So what's the time needed to perform this transition and how this transition occurs. So there are several ways to study this problem. A first one is the study of hydrodynamic limits. Which is, okay, you want to focus on the evolution of the density of particles. Okay, and okay, let me say something. It's a talk about probability. Well, if you think about particles, well, they have elastic collisions. There is nothing random into that. But because they are small, somehow if you perturb just a little bit the initial position, somehow you modify a lot the first angle of collision, and therefore thinking about this collision as random does not seem unreasonable. It's just because you lack information on the initial condition of the system, and it makes it much easier to study. So this would be a random evolution. Okay? So hydrodynamic limits, it's the evolution of it's the study of the evolution of particle density. So you make the number of particles tends to infinity, and you prove some kind of law of large number for the density of particle, and somehow it should satisfy some kind of PD. Okay. And another point of view, which is not unrelated, is the study of mixing time. And instead of looking just at the particle density, we want to know about really the full information about the system. So we look at the probability distribution of the particles. Okay, I mean, the particle configuration will have a probability distribution on the whole set of particle configuration. There will be an equilibrium distribution for this set of configuration, and you want to know how far one is from the other. So. Comparing probability distribution. Okay, and what I want to talk about more precisely today is the case of some asymmetric process. So you can think that somehow particles are forced to go more to the right than to the left So you can say that you have, okay, imagine that you have particles that are electrically charged and that you have some, okay, electric field in some direction. I don't know, that forces the particles to go to the right. Okay, and the reason why studying the asymmetric case can be interesting is that somehow it gives rise to different phenomena. So when you are in the symmetric case, when you have no fields, typically the evolution of densities are given by smooth equation because you have a diffusion term. And when you are asymmetric, you have gradient equations, so you have much more irregular things and you can create shocks and this kind of stuff. Okay, and so somehow also for the mixing, things will occur with a different pattern. Okay? Okay, so this is the global picture, but now we'll define you the process, which is somehow much more simple than that. So, okay, we have a segment with n locations. And on each location, well, I can have either one particle or zero particle. Okay, so I will call omega nk the set of particle configuration with I equal 1 to n of psi I is equal to 2k minus n. So I look at the set of configuration with k particles, okay? Ones are particles and minus ones are empty sites. And I assume that all the particles perform independent random walks. They jump to the right with probability p and jump to the left with probability q, where p plus q is equal to 1, and we are in some asymmetric case, so we assume that p is larger than 1/2. Okay? And you have some exclusion rules, so in order to maintain at most one particle per site, when a particle tries to jump on a site which is already occupied, the jump is just cancelled. Okay? So I will tell you later who this guy is, but it's general for this kind of process, if you don't take some things too crazy, that you have one probability distribution on the state space which is invariant for the dynamics, meaning that if you start with this distribution, then at any time you will preserve that distribution. Okay? And okay, so if we call eta t psi our process starting from initial condition psi, and pt, okay, so it depends on n and k, psi prime, what is called the Markov semigroup associated to it, which is just the probability that starting from psi, you are at configuration psi prime at time t. What is known is that the limit when t goes to infinity of pt psi prime is equal to pi nk of psi prime. So that somehow this distribution is not only invariant for the dynamics, but also when the time goes to infinity, the distribution of the system goes through this, converges to this equilibrium distribution. And what we are interested in is, okay, what time you need to be close to this guy. So for this, we need the notion of distance on the set of probability distribution. And okay, you might say all the distances are equivalent, but as we are taking n and the number of particles and the size of the system to infinity, somehow the distance, the choice of the distance matters very much. And we choose to study this problem with a total variation distance. So, okay, the total variation distance between two probability on omega is simply the maximum of the difference of the probability of two events. Okay, and because these things are probability and you can replace A by its complementary, it's a symmetric definition. Okay. And okay, we define the distance to equilibrium at time t as the maximum over all initial configuration of the total variation distance between pt psi and the equilibrium distribution. Okay, so we know this goes to 0, but somehow we want to know when this starts to be close to 0. Okay? And this distance, it somehow measures how well you can couple the two probability measure. Okay, how you can construct both so that they coincide with maximum probability. Okay? So, what we want to know about is the mixing time, which is the first time for which this distance goes below some threshold epsilon. Okay, where epsilon is arbitrary and is between 0 and 1. And okay, and you will see in a moment why I do not focus very much on the role of epsilon. Okay, so so this is what is called ASEP, so Asymmetric Simple Exclusion Process. Before stating the result, I need to do two things. First, tell you who's the equilibrium distribution, and tell you briefly what is bias card shuffling. So, so to describe the equilibrium distribution, it might be good to define the height function associated to a particle configuration. So given x and given a particle configuration xi, I define h, well, should I define it? H xi as the sum from y to x of xi y, which is just, okay, it's just a function that goes up. Okay, I should, maybe I will draw it here. Just a function that goes down by -1. No, it's a bad idea. It goes down by -1 when you have a particle, and by +1 when you have an empty. By -1 when you have an empty side, and by +1 when you have a particle. Okay, so you have a. So it starts from 0, and by definition it ends up at 2k minus n. Okay, and somehow it has to stay within this rectangle. Okay, and you can define v of xi as somehow the volume below the maximal configuration. Okay, I'm sorry for the ugly picture, which is basically the number of movements you need in order to go to the maximal configuration. And if you want to describe simply the equilibrium measure, it's just It just gives to every configuration a weight proportional to P over Q minus to the power minus the volume. There. Okay, so what I wanted to say is that our equilibrium distribution is very much concentrated on configuration with small volume there. So it will be, I mean, somehow the topmost configuration has positive weights, okay, and the distribution is concentrated on the finite neighborhood of that thing. Okay? So basically the mixing time is the time you need to reach somehow this neighborhood of the top mixing, of the top configuration. Okay? So now let me So what is bias card shuffling? Okay, 2 and 5. Okay, so instead of having configuration with -1 and 1, your state space is just a symmetric group. Okay, and how you display it is just you take a segment of size n, and you display numbers between 1 and n on it. And what we do is that, okay, with rate 1, you will, so each edge will be updated with rate 1. And when you update an edge, what happens is that with P, you choose to order the edge. And with Q, somehow you, how did I say that? Okay, you reverse order the edge. So sorry, that's really ugly, but the idea is how you sort. You sort the content of the edge and you unsort it. Meaning that here, if I select this edge, I will just take a bias coin with probability P. I will take these two numbers in increasing orders. So I will just do nothing. And with probability Q, I will just choose to put 8 before 4. Okay, and then I get a new configuration. And I wait until the next clock rings, and I do the same thing. And if you think about it, if you look at the evolution of the particles labeled from 1 to k, what you get is exactly the ASEP. So this Markov chain is just somehow, well, something that contains all the information about all the ASEP for all values of k, all the ASEP for all values of k. Okay, so I think now I'm ready to state the result. So the first thing is that the limit when n goes to infinity and when k over n, okay, so it's valid for all epsilon in 0, 1 and all alpha in 0, 1, where alpha is a parameter that goes, that's encode the particle density, the asymptotic particle density. So the limit of the mixing time when the particle density goes to alpha and when n goes to infinity is well, first you have to divide by n to have a non-trivial limit. The mixing time is of order n. And the limit you get is square root of alpha minus plus square root of 1 minus alpha squared divided by p minus q. Okay. Second, if you look at the mixing time for the bias card shuffling, what you get is that this is equal to 2 over p minus q. So somehow it's just what you get when you maximize this thing over alpha. So I mean, this mixing time has to be larger than this for, I mean, it is larger than this one for every k, because this contains the information about this first system. What it tells you is that if you want to mix all things simultaneously, you just need to mix the longest one, which is the one that takes the longest time, which was not a priori obvious. And the last thing is that, okay, we can identify also the rate at which the distance to equilibrium goes to 0, which is something called the spectral gap. So if you look at the distance to equilibrium, either for the ASEP or for the bias card shuffling, so we'll just put some n here. This is equal to, so here I just have the exact value, not the asymptotic behavior when n goes to infinity. And it's equal to square root of p minus square root of q square plus 4 square root of pq sine pi over 2n squared. Okay, so yeah, I think I don't have much time left. So, okay, so what I would have done if I had more time, but I can say briefly, is that this expression might seem a bit mysterious, but it's not very hard to explain. If you look at the evolution of this height function somehow, you can derive a scaling limit for that process. And this is just the time needed for this scaling limit to reach the top. So somehow it's obvious that this thing is a lower bound because, if you do not reach the top, then you need, then you're sure that you're not mixed. Somehow, and that's maybe the most delicate part of the work, we can show that this is also an upper bound, so that when you're macroscopically mixed, somehow you're also microscopically mixed. Okay, and I will stop here. Thank you very much. Explain in details. So let me focus on the case p equals 1, where the result is actually not really ours, but it can be derived as a corollary of a result of Rost from 91. Okay, so what Rost studied was a system where somehow you started from infinitely many particles on the right, okay, and let it evolve. So if you look at this in terms of height function, well, you start with this big corner, and each time you can flip a corner up, you do it with probability with rate 1, okay, and you let this thing evolve. So after some time, you will have something like that. And what Rost proved is that, so I will call this process, I don't know, h infinity of tx, okay, this height function, and I will, for simplicity, I will set the origin there. And what Rost proved is that the limit when n goes to infinity of h Tn xn divided by n was equal to, so let's see, t over 2 plus x squared over 2t if x is smaller than t in absolute value, and just x if x is larger than t. Okay, so actually you don't need two parameters here. You could just take t equals 1, it would just give you the same information, but I prefer to have two parameters here because, okay, I will need it to compare it to. So what Ross result tells you is that, okay, after some time, your process is well approximated by some parabola that is tangent to this axis. Okay. And now if you look at the process on the finite segment, well, somehow you can couple it with this infinite process just by saying that, okay, the height function you should have for it is just the minimum of this orange line, and, well, it's just what you obtain from the orange line if you had the constraint that you have to stay in this box. Okay, and yeah, the reason is that, well, you can check that the transition are exactly the same for the two dynamics. So for p equals 1, it means that lambda is equal to infinity. It means that the equilibrium measure is just a Dirac mass on the top. So the time to be at equilibrium is just the time at which you reach that. And the time at which you reach that is the time at which somehow the parabola gets strictly higher than this point. Okay? So then, in order to compute the asymptotic of the mixing time, you just have to try to find that at which time this point belongs to the parabola, because you know that immediately afterwards you will be mixed. Now the coordinates of this point are, okay, so I think here you should have 1 minus alpha, and here you should have alpha, okay? Because here you have n minus k, and here you have k. So, okay, if you sum the two, you get 1. And if you take the difference, you get 2 alpha minus 1. Okay, so this is 2 alpha, well, either 2 alpha minus 1 or 1 minus 2 alpha. It won't make a difference. So for this guy to be on this parabola, it tells you that it must be a solution of, okay, so t must be a solution of t over 2 plus, so what is x? X is this guy, 2 alpha minus 1 square over 2t is equal to 1. Okay, and if you look at this equation in t, this is just a second degree polynomial. Well, if you multiply everything by 2t, okay, the right solution you have to consider is just this one, so that you get the asymptotic of the mixing time is asymptotic to n times this. Okay, so what is different when p is smaller than 1? So first thing is when p is smaller than 1, somehow you can't couple these two dynamics. Okay, well, you can couple them. Okay, no, there are more different than that. So first, when p is equal to 1, when p is smaller than 1, this result, well, still holds, but was not proved in 91. So we still have hydrodynamic limits. Okay, but this was proved later. It's by Reza Klanou. But somehow, okay, you can't couple the two processes. The reason is that at some point, the boundary may push you down, okay? If you look at this process in infinite volume, you know that, well, if you look outside of this domain, it might be higher than the blue one. And for this reason, if you have this kind of configuration, the blue one can go down and the, okay, so this infinite volume thing gives you some upper bound on your process. So somehow, okay, because you still have the hydrodynamic limits and you still have this upper bound, you can still get a lower bound on the mixing time because you can get a lower bound on the time that the blue guy reaches the top. Okay, so. Okay, and now if you want to transform, to show that, to get a matching upper bound, you have to do several things. So first thing, you have to show that, that this thing is still the scaling limit for the blue guy. And somehow, there is no direct path to do it, so what you really have to show is that the blue guy satisfies some kind of differential equation with some adequate boundary conditions. Okay, and what we show is that the particle density satisfies some equation. So the derivative of the blue guy satisfies some equation. That's why the boundary condition is not that obvious. And then you have to check that microscopically the things are going well. So that, I mean, for instance, if you look at the scaling limit, it does not give you information about the position of the rightmost particle and the leftmost empty site. So you have to check that these things are really where they should be in order to then show that your system is well mixed. Okay, and I think now the time is over, so I will stop.